Welcome. We're now in chapter 3 and we'll be treating number system and algebraic structures. Systems, there's aspects in here, okay? Number systems. Okay, again, I'm Dr. Lois Adewoye Ademola. And in this is chapter 4, sorry about that. In chapter 4, we'll be considering a classification of fundamental sets, properties of integers, rational, real, and all the other topics. As you can see, they're key topics, examples and lemmas. Okay, and on the screen we have a diagram, kind of a flow chart of how the numbers are interrelated. Okay, we have complex numbers and all of complex numbers as defined, imaginary numbers. I'm sure you've seen all of this in your secondary school days. Okay, and how they are subsets and interrelated. We'll be using some of the screen later, so you need to know the definition of all these numbers by heart. You did that in your 103 maths 103. You did that had to do with numbers and systems of numbers. Okay, so you can pause the video or pause the screen and study and know all of the numbers and recall what you've been taught previously. Okay, so we begin with properties of numbers. Now, the set of integers, as we can see here in the previous slides, that the set of integers is basically consists of numbers, natural numbers, positive numbers, and negative and zero. So they have natural numbers, which include the positive, the negative, and the zeros. Those are a set of integers. We have the negative integers, we have the whole numbers, which consist of 0, 1, 2, all the way to infinity, and then the zero itself, and what we call the set of natural numbers, which are the positive integers without zero. Okay, so the set of integers, which is this z you see there, emits three operations, and they are the addition, subtraction, and multiplication. Now, there are 6 properties that they satisfy. What we call the associative law, commutative law, existence of a neutral element, existence of additive inverse, distributive law, and cancellation law, which is as defined here. Okay, so all you need to know is know all of the 6 properties by heart. Okay, so integers satisfy all of this. Okay, associativity, commutativity, existence of neutral element, existence of an additive inverse, distributive law, cancellation law, which is what you have here, 6 of them. Okay, so let's move to the next slide. Now, the set of integers, they are called rings because of the laws 1 to 5 that they satisfy. Remember, 1 to 5, that's from here, all of these 5 laws. Once they satisfy these 5 laws, which is what they satisfy, they are called what? They are called rings. See there? They are called rings. That's the name. So if I say one is an integer called a ring, you just say it satisfies the 5 identities, okay, which we had listed earlier, which are the associative law, commutative, existence of a neutral element, existence of an additive inverse, and a distributive law. Okay, so because it satisfies those 5, they are called what? Rings. Now, the cancellation law can also be expressed in this form. The cancellation law can be expressed as what you have here, meaning that if x is not equal to 0 and y is not equal to 0, then x times y is not 0. Okay, that's another way of writing this cancellation law. Let me clean the screen. This cancellation law down here, the cancellation, that's the point, the identity number 6, right? So another way of writing that same law, you can see here, you can write it as y plus z equals to y plus z, then y equals to z, x equals to y, and that's the first identity. The second identity, so you have xz equals to xy, and x is not equal to 0, then x is equal to y. So another way of writing it is what we have expressed here on the screen here. Okay, now this is so because the set of integers also satisfy this law, and if it satisfies this law, it is called an integral domain. So when is the set of integers called a ring, it satisfies the first 5 identities, right? It is also called an integral domain because it satisfies all 6 identities. Okay, so it's called an integral domain. That is, it has no zero divisor. Okay, now there's something called, which you should be able to state by heart, which is the trichotomy law. The trichotomy law simply says that every real number is 0. Well, 0 negative, so let me take it again. Every real number is negative, 0 or positive. Okay, every real number. That's the trichotomy law. So that's 3 major things that are trying it. It is negative, it is 0, and it is positive. Okay, the next thing you need to know is that the set of rational numbers, which is denoted thus with the Q. Let's go back to the diagram. So rational numbers, see rational numbers here. Okay, the set of rational numbers, they satisfy identities 1 to 6 as listed earlier. Okay, they also satisfy these identities. Every non-zero rational number x has a unique multiplicative inverse x inverse such that this identity holds. Okay, so we now know that the set of integers, when it satisfies the identities 1 to 5, associativity, commutative law, existence of a neutral element, existence of an additive inverse, distributive law. Once it satisfies this, we call it a ring, right? That's what the set of integers is called, a ring, right? Now, if it satisfies the ring, right? If it satisfies all the way to the 6th one, the cancellation law, it is what? An integral domain, right? That's what we said. It's called an integral domain. Okay. And for the set of rational numbers, we said it satisfies all 6 too, right? We've not given it a name yet, so let's just keep watching. I'll explain everything. Okay, it satisfies all 6 identities. In fact, that for any non-zero element in it, x, that you can, it has an inverse, x inverse, and it satisfies this identity. Okay. Now let's do some definitions. Okay, shall we? Now, I think, okay, good. So that identity is called the 7, identity 7. Did you see that? Where you can take the inverse and multiply by the non-zero element, the inverse of the non-zero element, and give you back the identity 1. So that is identity 7. So let's move forward now, shall we? Okay, so since rational numbers satisfy identity 1 to 5 and 7, okay, they satisfy these conditions, they are called fields. So it's called a field, okay, or a commutative division ring. So here, what is a commutative division ring? You're referring to a rational number that satisfies the first 5 identities and the 7th identity where we talked about the inverse. Is that not so? Now, real numbers also satisfy identities 1 to 5 and 7, and they are called fields too. So how many, we now know that the integers are called rings, right? When they satisfy 1 to 5. We know that the integers, if they satisfy identity 1 to 5 and 6, they are called integral domains. Now we know rational numbers because they satisfy identities 1 to 5 and 7, they are called fields. Real numbers satisfy identity 1 to 5 and 7, they are also called fields. Complex numbers also satisfy identities 1 to 5 and 7, and they are also called fields. So now you know that the rational numbers are called fields, real numbers are called fields, complex numbers are called fields because they satisfy identity 1 to 5 and identity 7. Now, the real numbers are subsets of the complex numbers. That's true. Let's see the table and let's see the flow. You can see that the real numbers, they are actually subsets over here. Let me clean the screen so you can see everything well. So truly the real numbers right here, they are subsets of complex numbers. And we know the complex numbers are fields, right? We know it's a field. And this is contained in it. So because this is contained in, it's also a subfield of the complex numbers, because the real numbers are fields themselves, aren't they? But when we're referring to them in the context of the complex numbers, they are called subfields. Okay, so that we know now. So you need to know these identities, the definitions, and know them by heart. Okay, let me check, go back a little. So we're through with the definitions for fields, subfields. Okay, the next thing you need to know are what we call an algebraic structure. What is an algebraic structure? So a non-empty set S equipped with one or more binary operations, say asterisk. So you can have a non-empty set S, say S, and it can have a binary operation, say plus and minus. So this is called an algebraic structure. Okay, so let's see the definitions properly. So we say a non-empty set S equipped with one or more binary operation, say asterisk, is called an algebraic structure. Okay, so in our case with the binary operation asterisk, this is how it will be denoted. Okay, so if the set of real is equipped with the binary operation addition, then its algebraic structure will look just like this. We'll write it as this, a set of reals with the operation addition. Okay, so now we know what an algebraic structure is. Now, an algebraic structure, which means we have a set, a non-empty set, with any form of binary operation, so we called it asterisk. So this kind of algebraic structure, it is called a loop if it is closed. What do we mean by closed? That is, if I have elements A, B in my set S, if these two elements play together or are related by the binary operation, the answer you will get must be in the set S. So if this holds, we say that algebraic structure S under the binary operation asterisk is closed. That is, it is a loop. So it will be called a loop. Okay, for instance, if I have a set, say S, with elements 1, 2, 3, and I say, is this set closed under the algebraic set closed under S under addition? Now look, if I pick two elements, say 1, 2, with the binary operation in S, with the binary operation addition, you say, oh, that's true, 1 plus 2 will give me 3. 3 is in the set S. You want to say it is a loop, right? But you have to check all the elements, because if I check 2 plus 3, this is 5. 5 is not in my set S, therefore it is not a loop. It is not closed, so it is not a loop. Okay, so that's how you check for if it is a loop. So the next definition is, if you have the same binary algebraic structure S with the binary operation asterisk, it is called a semi-group if it is closed, meaning that if I pick two elements in it and it relates by the binary operation, it will still be in the set, right? It's associative, meaning that if I pick two elements A, B, C in my set S, if I take A with the binary operation B asterisk C, remember associativity, whatever answer I get here must be equal to the answer when I combine A asterisk B asterisk C. If these two answers on both sides are equal, then we say, and it is closed. First, you must check for closure. That is, we pick two elements A asterisk B. If it is in the set S, then you say it is closed. And then you will now check if associativity will hold in that set. If that holds, associativity and closure, then we say we have a semi-group. Okay? Once those two identities hold, we have a semi-group. Don't worry, I would explain them using an example later, but know this definition and have an understanding of them. The next one that you need to know is what we call a monoid. For a monoid, it means that it is closed, meaning if I pick two elements, it will be contained in the set S. Associativity, if I pick three elements, it will satisfy the associativity law. And there exists an identity element, meaning that if I pick A in my set S, there exists some, say M, such that A under the binary operation M must give me back A, and M under the identity A, asterisk with A, must give me back A. So it means that M is my identity, right? Because I'm always getting it back. It's like looking into a mirror. If that exists, these three identities, closure, associativity, and the existence of an identity, we say the algebraic structure S under asterisk is a monoid. The next definition you need to know is what we call a group. For this algebraic structure to be a group means it must be closed, it must be associative, there must exist an identity, and there must exist an inverse. Meaning that the identity 7, remember identity 7, if I happen to have an element A, there will exist an inverse, say A inverse, such that I will get back my identity. You could call it 1 or E. In algebra, we use E most times to denote identity. Also, if I take A inverse, asterisk A, it will give me back E. If these two conditions hold and it is closed, associative, and it has an identity, then we say the algebraic structure, this algebraic structure is a group. So you need to know the definitions, each one of them. Okay, so with that definition sorted, let's move forward. We have an example here now. For this example, we're told to check if the multiplication is a binary operation on the following set. So our binary operation is multiplication times, okay? And our set is A. So we want to make it in an algebraic structure, right? So we have A and then comma asterisk, right? So this is an algebraic structure. We want to check if it's going to be what the binary operation. Check if the multiplication is a binary operation on the following set. So to check if it's a binary operation, basically check if it is closed. That's what we want to check. So we pick every element. So we start with number 1. There are 2 elements and 2 elements here. We combine them together. So we checked 1. So see what has been done. We first solve A first, the A part, not the B part. Let me confirm that my elements are correct. Oh yes, sorry. The solution for this set is for B. This is B. This is B, not A. B elements are in B, not A. So this is for B because that's the set for B. 1 and minus 1. There's no minus 1 in the A here, okay? And therefore this is A. This is A. Sorry for the typo, okay? So this is set A. This is B, okay? Sorry, this is A. No, this is B, right? Correct. Okay, so let's continue now. So we want to solve the B first since I've interchanged them on the slide here. So we're solving B first. So we pick all the elements and combine all possible combinations we can get. We have 2 elements, 1 and minus 1. So we check 1 times minus 1. We'll find the value. Multiplication is this thing. We check 1 times 1 because that's the other combination you can have. We can have minus 1 times minus 1, right? We check because there's 1 minus 1. So these are all the possible combinations. You agree with me that 1 times minus 1 is going to give me minus 1. Is the answer in B? Yes, it is because there's minus 1 in B. So this is done. 1 times 1 is 1. Is the answer in B? Yes, it is. So done. Minus 1 times minus 1 is positive 1. This is also in B. Therefore, you agree that B is closed. So that's why we say it is a loop. So B under the binary operation times is a loop. The algebraic structure is a loop. It's a closure. Okay, that's what we mean there. That's what I have solved here, but unfortunately my typo had interchanged the lettering, so let's be careful with what I have done there. Sorry about the mix-up. So it is not A, the values are interchanged. Okay, let's be careful. Okay, continuing with the next example, the second one. In the same way, we look at the 2 elements. So our next one is A actually, so we're solving for A. A has elements 1, 3. What are the possible combinations? We have 1 times 1, 1 times 3. What else? 3 times 3, right? Yeah, that's all. We've done 1 times 1, so that's all. So 1 times 1 is 1. Agree? Is it in A? Yes, it is in A. 1 times 3 is 3. Is it in A? Yes, there's 3 here in A. What is 3 times 3? 3 times 3 is 9. This is not in A. So the algebraic structure A under multiplication is not closed. It's not closed. And if it's not closed, it is not a loop. Okay, it is not a loop. So the binary operation is not defined on the set A. So that's how the examples go. So just be careful. I've mixed the two sets. We work with, I interchange the sets. Okay, you can try. If you have questions, ask via the WhatsApp group. Okay, thank you. Okay, let's move forward. The next example before says we should determine if the algebraic structure on the set of natural numbers and our binary operation is addition. So what are natural numbers? I have cut a part of the previous diagram we had at the beginning here. Natural numbers are basically just positive numbers, right? So positive numbers of integers, which are the 1, 2, 3, 4, and we keep going. Okay, those are the natural numbers. Okay, now that we know that, we want to check if it is a group. What do we need to show something is a group? Let's go back to the previous slides where we defined group. To show something is a group, we need to show that it is closed. We need to show it is associative. We need to show that there exists an identity, and we need to show there exists an inverse. So let's go back and see how to solve it. Okay, sorry. Okay, so first thing we need to do is check for closure. So we will have to verify if it's closed, associative, if there exists identity, and if there exists an inverse. So that's what we want to do now. Okay, so clean it. So we want to check that, and we know what natural numbers are. All the elements are from 1 all the way up. So for closure, we pick any two elements. So we pick x and y from the set of natural numbers. And we can see that no matter what x and y I pick, for instance, if I pick x to be 1 and y to be 3, which is what I have here, and the binary operation again is addition. If I add 1 plus 3, it will be 4. 4 is always in the end. Is that not so in the set of natural numbers? And guess what? It is true for all x, y in my set of natural numbers. So if it is so, it means that it is closed, and hence it is a loop. So we've succeeded in showing that this structure is a loop. But our target is to show it is a group, not a loop. So we check the next property, which is associativity. For associativity, we pick 3 elements, x, y, and z, in the set of natural numbers. And we check if I sum associative, check the identity on the left, check the identity on the right, and see if they will be the same. In particular, we now consider that elements. We said let x be 2, y be 4, and z be 5. You can choose any value of your choice, noting that you are picking elements from the set of natural numbers, which are 1, 2, 3, all the way to infinity, right? So I have chosen those 3 elements. And I checked here. If you check, 4 plus 5 is 9 in the bracket here, considering board maths. And 9 plus 2 is still going to be 11, right? Again, 2 plus 4 is 6. 6 plus 5 is 11. So therefore, my right-hand side and left-hand side are equal. And the answer 11 is in the set of natural numbers. Therefore, it is associative. And this is true for all x, y, and z in the set of natural numbers. You can verify that yourself. Pick any value of your choice, noting that you are picking from the set of natural numbers. It has no negative numbers. It has no 0. Okay, so you have to be careful when you're doing that. So we've seen that it is closed, meaning it is a loop. We've seen that it is associative, meaning that it is closed and associative. Therefore, we are shown that the set, our algebraic structure, is a semi-group. Again, that's not all we want to show. We want to show it's a group. So we still have 2 more identities to check for. We have to check if we have the identity element and the existence of an inverse. Now, is there an identity element? Oh, no, there isn't, because the only identity we normally have for addition is the element 0. And 0 is not in the set of natural numbers. Therefore, it has no identity, so it is not a monoid. Guess what? Once you get to this place, you don't even need to check this inverse part for you. Why? Because you have found that it is not a monoid, it cannot be a group. But I've gone further to check if it is if it has an inverse. But it cannot have, because if you have positive numbers and your addition is positive, you need negatives to get 0, right? And the identity doesn't exist. So therefore, it is not a group. So that's how we concluded that the algebraic structure is not a group. Okay, and that's all to the proof. You can try the same example for the set of integers yourself under addition. You can check for natural numbers with a negative sign and see whether you get something. Whatever you do, you can send your solutions to me via the WhatsApp group, and let's see how I can help you there. Okay, so we can discuss it. Okay, let's move forward. And finally, we're considering a lemma here. The lemma says that the square root of 2 is an irrational number. We want to prove that it is an irrational number, so we prove by reduction ad absurdum. If you remember in the previous videos, we had discussed the different kinds of proofs as a proof by contradiction. Okay, so we suppose that it is rational. I know what rational numbers are. Rational numbers are numbers that you can write as a fraction, a over b, right? Where b is not equal to 0, right? So we will assume that it is rational. So if it is rational, we can write that root 2 will be equal to, say, x over y. Y not equal to 0, right? So that's why I wrote here x and y there. Now, and we make sure that x and y are at its lowest form, meaning I cannot divide, say, okay, 2 go, 3 go. No. It's at the lowest. The smallest form it can be, say, 1 over 3. Okay? So, say, I don't know. We're just assuming it, and we're making it to be the smallest possible it can be. So if it's the smallest, if I want to make 2 come out without the root, you just square both sides, right? So if you square both sides, you get 2 equal to x squared over y squared, right? Okay, so that's what you see right here. Squaring both sides, okay? So let me clean this so we can flow with what I've typed right here. So I haven't squared both sides. I want the letters to be on one side and letters separated on both sides of the equation. So all you do is cross multiply, right? If you cross multiply, you get 2y squared equals to x squared. You just cross multiply, okay? So that's how we got that. But then because there's 2 in front of this, it means it's an even. It means 2 in front of the y squared means that x squared is even, right? So x squared will be even. So it must be x, okay? So we can write x to be some number, say x equals to 2m, because we said it was even 2, because we had seen that x squared was even, right? Okay, so if x is even, and we've given it this value, all we just do is substitute wherever I see x in my earlier equation up here. I'll substitute x value to m wherever I see x. So now, okay, yeah, which one did I use? Okay, I used this. This was the one I used. So we just substitute wherever I see x in here, I'll put 2m. So that's how I was able to write, where am I? It's because by adding both squared, we get x squared equals to 4m. So you understand what I've done here. So if this is x equals to 2m, what's x squared? X squared definitely going to be 4m squared, right? Okay, so substituting wherever I see x squared, the value 4m squared. So remember, this is what I said I'm substituting into. So see it right here. Okay, so I substitute this value for x squared, and that's how we got what you see here. Okay, so if we do that, if you divide both sides by 2, you have what we have, y squared equals to 2m squared. Wow, it means y squared is even 2, right? Is that not what it means? So if y squared is even, x is even, it means I can write y something like, say, 2n, right? Because it's even. But then, is that not a contradiction? Because guess what happens? If I do x over y, this will be 2m over 2n. But we said that x over y is at its lowest term, which means, but this is a contradiction. I can cancel out 2 here, which wasn't supposed to be possible, which means I have a contradiction there. So let's see how I concluded in the proof of the theorem. So, again, y squared is even, so y must be even. So both x and y are even, thus x over y is not in its lowest form, which is a contradiction. So we reach our contradiction, meaning that root 2 is actually irrational. And that's the end to our proof. Okay? Thank you. And again, ask questions in the video, on the video in the chat, and also try some examples. I'll give us exercises during the practical class. Thank you.